I'm reminded, as I start this video, of Calc 3, in which we kind of move through vector operations. We first talked about adding vectors and then subtracting vectors and then multiplying vectors by scalars, and we slowly got to how to multiply vectors by vectors. And actually, there were two different kinds. One of them was the dot product, one of them was a cross product. Well, we're doing the same thing right now, where we started with adding and subtracting matrices and then multiplying matrices by scalars. Now we're going to talk about how to actually multiply matrices. And without any further ado here, we actually have to start by reviewing something I just mentioned, which is the dot product. So remember, the dot product works by taking two vectors of the same dimension, right? The same number of coordinates. And what you do is you multiply the corresponding coordinates and then add the results. So A dot B is A1 B1 plus A2 B2 plus all the way out to AN BN. So here we go with two four dimensional vectors here. So it's going to be 2 times 1 plus 3 times negative 1 plus 5 times 0 plus 1 times 2, which is 2 minus 3 plus 2, which is 1. There we go. So dot products are fairly straightforward. And we're going to need them in our definition of matrix multiplication. Now, this looks very complicated, and like it is with all things in this chapter, doing it is one thing, and then trying to say it out loud and make it precise is another. So here we go. Let A be an M by R matrix, and B be an R by N matrix. Those sizes feel weird, and they are, but we need them to be just right. We compute A times B as follows. The ijth entry of AB is the dot product of the ith row of A with the jth column of B. So that means that the number of columns of A has to be the same as the number of rows of B, so that we can take the dot product of them and we'll have the same number of coordinates to line up. Okay, so here's what this thing looks like. We're not really ever going to come back to this and do it via the definition. Here's what it looks like in summation notation. Let me make a comment about size first. So these two things have to match up so that when we take the dot product of the column and the row, we end up being able to do it. And then the M and the N out here actually end up being the resulting size. Okay, so a M by R times an R by N ends up being an M by N matrix. So make sure the insides match, and then the outsides are what the size of the result's going to be. And let's try this. Let's go kind of slow through the first one, and I will show more work than I ordinarily do. So this is a 2 by 2 times a 2 by 2, which means that we are allowed to multiply, because these two are the same, and then the result will be a 2 by 2. All right, so in each of these coordinates now, in the first row, first column, I'm going to take the dot product of the first row with the first column. So I get 1 times 1 plus 2 times 1. And that's it. That's the first spot. What about the first row, second column? That's going to be the first row dot second column. And so I get 1 times 3 plus 2 times 1. There we go. Now what about the second row, first column? Second row, first column, I get 3 times 1 plus 1 times 1. Last but not least, what about the second row, second column? Let's dot those things. That's 3 times 3. I said 3, I wrote 1. 3 times 3 plus 1 times 1. And there we go. We've just done our first matrix multiplication. Let's go ahead and do all those now. And feel free to just skip all this work here. 1 plus 2 is 3. 3 plus 2 is 5. 3 plus 1 is 4. 9 plus 1 is 10. There we go. We just completed our first matrix multiplication. Let's move on to B here, and I'm going to illustrate something with B. So B is a 2 by 2 times a 3 by 2. So notice that these don't match. So we're not supposed to be able to multiply these, and let's just see what would happen if we try. If I try and do the dot product of the first row and first column, what do I end up with? And you can see here, I get 1 times 1 plus 2 times 2 plus something times 3, right? We can see here that we've got a problem, which is why the number of columns of A has to match the number of rows of B, okay? Because we're going to take dot product of row with column, and so that one does not work. I want to do the next example in reverse order here, so I'm going to do that one. Because what it is, if I just take those two things and reverse them, if I do a 3 by 2 times a 2 by 3, you'll see that this, not 2 by 3, 2 by 2. You'll see that this actually is allowed, and what I get left with is a 3 by 2. So let's see how this works. They don't have to all be the same size. They can be weird sizes. Let's see. So 3 by 2 here. Let's see how much I have to write. Okay, in the first row, first column. So first row, first column is going to be 1 times 1 plus 0 times 3. We can just go ahead and say that that's 1. Good. In the first row, second column, I have 1 times 2 plus 0 times 4. Well, that's 2. That's pretty straightforward, too. Okay, good. Now, you can just kind of take these and move them along, right? We're just going to keep going back and forth. We're going to go down on the first matrix, and we're just going to kind of alternate back and forth between the columns. So now I have 2 times 1, which is 2, plus 1 times 3, which is 3. Okay, next I'll move over. 2 times 2 is 4, plus 1 times 4, 1 times 4, which is 4, that's 8. Okay, now we're going to move down to the next row and first column. Okay, so what do we have here? 3 times 1 plus 4 times 3. 3 times 1 is 9, plus 4 times 3 is 12. It makes 21. And the last one, let's move that over. So I get 3 times 2 is 6, plus 4 times 4 is 16, which gives me 22. 6 plus 6 is 12. Okay, there we go. We just did our second matrix multiplication. All right, now this should sort of stand out. So we can multiply some matrices in one order, but not the other. That's very interesting. Okay, now we have some more examples to do, but I would like you to sort of pause and try this on your own. I would call the 3 by 3 times the 3 by 3. If you can get this one done, then you can generally do them all. And I don't know if I want to write all of the steps on this or not. So try and do it yourself, and then watch me do it. Okay, let's hope I can get it right. All right, so pause the video here, and then push play after you've attempted it. Okay, so hopefully you've attempted it now. Let's do this. So first row with first column. Okay, so 1 times 2 is 2. 0 times 1 is 0. 2 times 0 is just 0, so 2 plus 0 plus 0. Good. Move over. 1 times 1 is 1. 0 times 0 is 0. 2 times 2 is 4, plus 0 plus 4. Move over one more. This kind of helps if you can point to both of these at the same time. I don't have fingers here, but kind of what I do is I point to this with one hand, and I point to this with the other hand. And what I do is slowly move that and that and that and that, right? And sort of tap them at the same time. And if you can kind of get your hand coordination down, you can be very efficient at this. Okay, so then I get 1 plus 0 plus 4. Okay, move to the next one. And I'm trying to talk while I do all this. If I miss one of these, I apologize. Okay, next one. 0 times 2 is 0. 3 times 1 is 3, 0. So I get 0 plus 3 plus 0. Move to the next one here. Middle row, middle column. That's going to be 0 plus 0 plus negative 2. As you can see, a few zeros are really good to have around on this. Last one from this. 0 plus 9 minus 2. Okay, 2 times 2 is 4. 1 times 1 is 1 plus 0. 2 times 1 is 2. Plus 1 times 0 is 0. Plus 2 times 2 is 4. Last one, we're almost there. 2 times 1 is 2. 1 times 3 is 3. 2 times 2 is 4. Okay, now I just have a bunch of arithmetic to do. Two, 5, 5, 3, negative 2, 7, 5, 6, 7, 8, 9. All right, cool. Hopefully that worked out well. I have a few more examples here. Let's just kind of do this really quickly. I have a point to make here. With these two examples, A and B, I have 3, 1, 2, 5, and 3, 1, 2, 5, and 1, 0, negative 1, 2, and 1, 0, negative 1, 2. I'll show you the point I want to make here, but I want to multiply these two things in different orders. Okay. So they're both 2 by 2. And so when I multiply this, what do I get? All right. So 3 minus 1 is 2. Then 0 plus 2 is 2. Then 2 minus 5 is negative 3. And 0 plus 10. There we go. Good. Let's do this one now. So that's multiplying them with the 3, 1, 2, 5 on the left. Now let's do it the other way around. So 1, so it's going to be 3 plus 0 is 3. Oh, we can already see something's different here. And move to the next one. 1 plus 0 is 1. Whoops. Then I have negative 3 plus 4 is 1. One more. And negative 1 plus 10 is 9. Okay, here's my point about this. When we multiply these in different orders, we get different results. So the addition of matrices is cumulative, meaning, I'm sorry, not cumulative, commutative. Commutative, where I can multiply things in any, I can add things in any order that I want to, but I can see now that I cannot multiply these things in any order that I feel like. And I might ask, when have we seen this kind of behavior before? And I might remind you to how we did vectors with I, J, K. So the cross product, I think, was the last time that we saw something that was not commutative in multiplication. So, all right. Now that all feels very kind of strange, but does this actually tie back into what we're doing? And the answer is yes. Let me do this real quick, and then we'll end this second video here. So take a system like this. So 2x1 plus 3x2 equals 7, and 5x1 minus 4x2 equals 9. So let A be the coefficient matrix, find A. So we talk about A being the coefficient matrix of just the things on the variables. So 2, 3, 5, negative 4. Okay. So there's my coefficient matrix. All right. Now, suppose X is this column matrix. So X is 2 rows, 1 column. What is the size of AX? Well, let's see, that's 2 by 2 times, I'll put that symbol there, times a 2 by 1. They can be multiplied, and the result is 2 by 1. All right? So AX, right? X, a little vector symbol, because we called that a column vector, remember? So AX is a 2 by 1 matrix. Now let's find AX. Okay, so check this out. This is where it sort of starts to come to life here. 2, 3, 5, negative 4. If I multiply that with x1, x2, you get 2 rows, 1 column, all right? So the first thing is going to be 2x1 plus 3x2. Okay, what's in the next one? 5x1 plus negative 4x2, and I'll just write that as minus 4x2. All right, does that look familiar? I think the answer is yes. Check out where this thing came from. So we have 2x1 plus 3x2 and 5x1 minus 4x2. What we can do is we can just say, well, that first system over there is 2x1 plus 3x2 and 5x1 minus 4x2 equals, remember when two things are equal, so the same things in the equal things in equal coordinates. So that first thing is 7 and the second one is 9. So what we're going to do in general is say, we're going to say, well, let B be this vector that is the answer column over there. Then we'll say that AX is equal to B. And so that is how this multiplication of matrices gets along with the system stuff that we've been doing before. And in the next video, we're going to explore a little bit more along these lines before we move on to solving systems that are in this form. All right, I'll see you then.